right, 5.2, slope fields. Slope fields is made up of two words, fields and slopes. Fields and slopes. Okay? Now, slope, of course, implies derivative, and field, in this case, implies not like a large meadow or anything, but some region. Some region, okay? So we're going to be looking at slopes in a given region. Now, what slope fields are, and I'll mention this to you from the onset. Slope fields give us a way to visualize the slopes of a differential equation, okay? Slope fields give us a way to visualize the slopes of a differential equation. In the previous section, we were solving differential equations analytically, right? We were separating the variables, integrating both sides, and solving for y. And of course, once you solve for y, you can see what the family of general solutions look like with the plus c, or you can find the particular solution and sketch it. But not all differential equations are separable or solvable by analytic methods. And so the question then becomes, is there still a way to visualize the general solutions without having the equations? And the answer is yes, by way of slope fields. So what a slope field really is, it is a graphical solution to a differential equation. It's a graphical solution to a differential equation rather than an analytical one. And it's real easy to generate the slope field, okay? That's all that says right there. Now, you're probably familiar with slope fields. Sometimes they're called vector fields. Sometimes they're called flow fields. If you look at this map across the Middle East, those arrows do not indicate the gunfire. They indicate what? This is like a weather map. Wind, right? They're wind. And you've seen this on all kinds of weather maps. This is a vector field. So the longer the arrow, the more intense the wind. The shorter the arrow, the less intense the wind. And of course, the arrow points in the direction of the wind. So if you were a feather and you dropped in over here somewhere at Oman, you can kind of follow it around, and you can see how that feather might drift across the Middle East. So these appear a lot on weather maps and stuff like that. But this is essentially a flow field or a vector field. You follow the arrows. The only difference between a slope field and a vector field is in the slope field, we don't put little heads on the arrows, so we don't necessarily flow one way. We can flow either way. But if you drop in anywhere on this map, if you follow the arrows in any directions, you can kind of float around the region. For example, let's pick one. Let's try. Well, what's a good color that contrasts with all this? Beefy brown, green. Beefy green. There we go. If I dropped in right here, somewhere in Saudi Arabia, and I went with the flow, going right through Baghdad. Look out. Oh, now we're into Syria. Uh-oh, turn around. Now we're back in Syria. Uh-oh. We're caught in this vortex in Syria. Uh-oh. Turkey. Okay. Turkey. Oops. Yeah. I don't know. We're going up there. Okay, and if you dropped in over here, it looks like you're going to get caught in that Syrian vortex. Anyway, these would be the flow fields. And notice I didn't draw an arrow on it. You can go either way. So what I drew here would be a particular solution to a differential equation. The entire region itself would be the pictures of what the general solutions are. And depending on where you dropped in, that would be your initial condition. Once you drop in somewhere, you have your initial condition. You then go with the flow literally, and some of these are kind of tricky. You can kind of see where you end up with. And of course, we can go backwards, so we could follow our arrows in the reverse order. Something like that. That would be a particular solution. So the collection of all the lines themselves gives you the general solutions. So you can see what the solutions look like without finding the equation. Ours aren't going to be that elaborate or dangerous. Okay? Here's something like what we might have to do. Draw a slope field for the differential equation at the indicated points. All right, so notice that this is a differential equation. It's pretty easy, right? dy dx equals x squared. We have a coordinate grid given to us, and the indicated points are going to be the intersections of the grid lines. Okay? So how are we going to generate a slope field? Well, remember that a differential equation gives us a way to find the slope of the tangent lines at any point on the graph. And notice our function is just a function of x. So this is really just generating some points. What's the easiest value of x to plug in there? 0, okay? So when I let x equal 0, what's the slope when x is 0? 0 squared, which is 0. Very good. What does the slope of 0 look like? What type of tangent line? Horizontal line. So here's the thing. On my graph, when I'm generating the slope field, everywhere x is equal to 0, which is namely on the y-axis, I'm going to draw a little piece of a tangent line that has a slope of 0. I don't want the tangent lines to be too long because I don't want them to interfere with the other tangent lines I'm going to be drawing around that. I'm just going to draw it a reasonable size so that you can see that it is in fact a line and not a point, and that its slope is 0. So here we go. There we go. There's one. There's another one. There's another one. These are as horizontal as I can physically make them. How long do they need to be? Long enough to see, but not so long that they interfere with any other ones that you might be drawing. Easy enough, right? All right, notice now we can plug in a 1. When x is 1, because it's just a function of the x value, up and down vertically at the vertical line x equals 1, what's the slope? Well, what's 1 squared? 1. What does the slope of 1 look like? That's a big one, right? I mean, that's an important one because that's 45 degrees. 0 is a real important one because you could visualize horizontal. Slopes of 1 are 45 degrees. They're also very important. You draw them as close to 45 degrees as you can. And, of course, you can copy and paste on Notability, but you can't on an actual test. They should all be the same relative to each other, and they should all be as close to 45 as possible. All right, now when x is 2, plug it in. What's 2 squared? 4. The slope of 4 is going to be steeper than 1. Now, how do you measure a slope of 4? You don't. You just know that 4 is steeper than what? 1. So you go with it. Is that steeper? Yeah. If you don't think it's steep enough, make it steeper yet. Now, I'm going to cheat here because I don't want to zoom in and out and then have them all be different. But on paper, you can kind of reference it, and they should all be the same. All right, so those are all slopes of what I'm calling 4. Now, notice I didn't give myself much room. If I had to do one at 3, the slope of 9, I would pretty much have to draw it almost vertically, wouldn't I? You're not going to be asked to differentiate between too many different types of positive slopes. Maybe a 1 and a 4, and maybe a 1 and a 1/2. If you draw something that's less steep than 45 and something that's a little steeper than 45, that's reasonable. But it gets really hard to convey the difference between a slope of 4 versus a slope of 4 million, right? All right, now we work the other way. When x is -1, what's -1 squared? +1, right? So now that I've drawn all of these right here at 1, it's the same slope. I can really cheat with Notability. I can lasso that whole column, copy it and paste it, and then just slide those in there. That looks good. And now when x is -2, I plug it into my differential equation. What's the slope at -2? +4, which are the same ones that I drew right over here on this column. So this is where Notability is really nice. Okay, so there you go. Now I just generated a slope field. It's a field, it's a region, it's an area that has a bunch of little slopes drawn in there, little pieces of tangent lines. And what those tangent lines do is they indicate what the shape of the general solutions are. So if you were now to drop in anywhere into this graph at a particular point, you can go with the flow. Like let's drop in right there at -2, -1. The particular solution then would be what? How would you draw it? Well, go with the flow. Let's go to the right first. It looks like it's going to be coming up there. It looks like I'm going to go horizontal there. And then it looks like it's going to go up and it's going to increase. You want to draw it all the way through the points and then maybe draw a little bit going out here this way. Draw it all the way to the ends of the graph. When you're given a particular point, like -2, -1, that would be the only coordinate through which you're actually required to pass, because everything else is just literally going with the flow. Now, if you had to look at that particular solution in green, it kind of looks like it belongs to what polynomial family, what degree? It kind of looks like an x cubed, right? In fact, the general solution looks like a family of x cubes, and the only difference between one particular solution and the other is the what? the y-intercept, which would be the plus c, which in this case would be a vertical shift. It looks like they're all just vertically shifted from each other. Now, is that the case? Well, yeah, let's see. I gave you one to start with because it was easy to sketch, but it's also one that we can confirm. We can actually separate the variables here and find the general solution. So if I separate the variables, and again, this is not always the luxury that we have. I separate the variables, and then I integrate both sides. And what's the antiderivative essentially of 1 with respect to y? Y. And x squared becomes 1/3 x cubed plus what? C. And we've solved. So it turns out that the general solutions are the family of solutions that are the cubics that are shifted vertically. And you can see that in the slope field. We didn't really know anything about the general solutions. We were just plotting not points, but little slopes at particular points. Let's go ahead and figure out what the equation is of the particular solution. At the point -2, -1, we get -1 equals 1/3 -2 cubed is -8 plus c. So c would equal positive 8/3 minus 1, which is what? 5/3? So the equation that we wrote, or that we drew, was 1/3 x cubed plus 5/3. Now notice my y-intercept was supposed to be at 5/3. It looks like I drew it at 1/3. Is that okay? Yeah. Okay. As long as you're going with the flow, if you're given a point, that's the only one that you need to make sure you hit. Everything else, you're just kind of interpreting it, and everybody's is going to be a little bit different. The way that these things are scored is the following. If you have to generate a slope field, you better make sure your horizontal zero slopes are as horizontal and flat as you can make them. If you end up with a vertical slope, which remember is non-zero over 0, your vertical lines should be as straight up and down as possible. The other ones that should be pretty close are your slopes of 1 and, of course, -1, your 245. And then outside of those, everything else is just graded on a relative scale. Is a slope of 3 greater than 1? Is a slope of 4 greater than a slope of 3? So on and so forth. And then for the particular solution, did you pass through the point that was given? And did you follow your slope field all the way through from left to right? All right, pretty cool. You got the idea? A slope field is a what? It's a graphical solution to a differential equation. We saw the family of x cubed solutions long before we found, not long before, but shortly before we found the particular solution. Now this is particularly useful when you cannot find the antiderivative equation. And it's also particularly useful because you can program a computer to generate slope fields, because it is just mindless, numbing, repetitive work. And a computer can generate the graph of the solutions very quickly and easily, okay, without complaining. All right, so here is the same slope field generated with a math program called Mathematica for many, many more points. And if you include more points and more slopes, of course, the general solutions manifest a little bit more readily. In fact, if you included so many points that each of the tangent line became smaller and smaller and smaller as to not interfere, it becomes almost a dot. And of course, when you connect the dots, you actually get the picture, right? So there it is. It's indubitably a cubic function. All right, let's try this one here. Example 2. Sketch the graph of the solution for the non-separable initial value problem. Now, if it's a non-separable differential equation, guess what that means? We are not going to be able to separate the variables, which means we are not going to be able to solve it. We are not going to be able to get y equals. But does that mean that we're not going to know what the general solutions look like? Nope, because we have another way to see the solutions without knowing what the equation is. It's called a slope field. So here we go. Y prime equals x plus y. We're not going to worry about the particular solutions, and I think this should be a negative, until we graph the entire slope field, which is the general solutions. Okay, now there's a couple of ways to generate slope fields. You want to look at the graph that's given. Okay, so you're going to be given some indicated points. You can assume the scale here is 1, So we're going all the way out to x equals 2 and negative 2 and as high as y equals 1 and negative 1, including the origin. You could just randomly pick a point, let's see, the point 1, 0, and go over there and plug it in and get the slope and graph it. But you want to be a little bit smarter about it. Your zero slopes are pretty important. So ask yourself this first question. For what values of x and y is y prime going to equal 0? X plus y is equal to 0 when x and y are what? Opposites of each other, right? So when y equals negative x, would you agree? Now what does the line y equal negative x look like? It's everything along that negative diagonal, right? So everywhere along that negative diagonal, you're going to have slopes that are 0. That just speeds up the process, okay? So here's 0, 0, horizontal. Here's negative 1, or 1, negative 1. Here's negative 1, positive 1, okay? Now, you don't have to do it that way, but when we're doing this in reverse and we're trying to recognize slope fields from an equation, that's one of the things you look for. Where do you get the 0 slopes? When x and y are opposites, okay? So right along this negative 1, 1 diagonal. What else can we do? Is this ever undefined? X plus y, is it ever undefined? Because those would be possibly vertical slopes. No. So now we can go ahead and just pick a point, like the point 1, 0. The point 1, 0, you plug it in, what do you get? What's 1 plus 0? 1. That's another important one. That's your 45. Actually, you got to aim it from here. You got to aim it towards that point. That's your 45 on this scale. 45. Okay, cool. What about the point 2, 0? Well, that's 2, right? So how are we going to draw a slope of 2? A little bit steeper than 1. There's 1, there's a slope of 2, a little bit steeper. All right, so just randomly, how about the point 0, 1? That's also 1. So this one and this one need to be the same steepness. If you don't think they are, try it again. In fact, I'm going to copy and paste it. Now notice I'm seeing a pattern here. I have zeros down this diagonal. I have a 1 and a 1. Maybe this one's a 1. What's the ordered pair there? 2, negative 1. What's 2 plus negative 1? 1. So it looks like this function is getting these patterns all along the diagonals. So if this was a slope of 2, maybe this diagonal has a slope of 2. Let's make sure. That's the point 1, 1. What's 1 plus 1? 2. So with notability, even when you're doing your homework, you can copy and paste. Makes it a little bit easier to make sure that they match. If you're doing it on paper and you have the whole thing in your perspective, just make sure that all the slopes that are the same magnitude are the same steepness as well. And the one up in the right corner, that's 2, 1. What's that? 2 plus 1 is 3. Now, it looks like that's going to be the steepest I'm going to have to go. So just to show that it's steeper than 2, it almost looks vertical. I'm running out of room, so I'm going to leave it like that. All right, let's see if the pattern continues along this diagonal. What's negative 1, 0? Negative 1 plus 0 is negative 1. A slope of negative 1 is a slope of negative 45, so it should look like that. And again, if you're drawing it on this scale, it should match up with this point right here. So let's see. From one dot to the other, something like that. And maybe copy that one. Okay, what's the next one? Let's see if the diagonal holds. Negative 2 plus 1 is also negative 1. And what about this one down here? 0, negative 1. 0 plus negative 1 is negative 1. Okay, yeah, there you go. The diagonal is holding. Negative 2, 0, that's negative 2. So I need to draw it steeper than negative 2. That's going to be something like that. And then you can verify that that's negative 1, negative 1. That's also negative 2. And that's going to be negative 3, which is about the steepest. I'm going to go in the negative direction. So I'm going to draw it almost vertical. So there's the solution, the general solution. You can kind of see the way it's flowing. You can imagine there's an arrow on either end. You could drop in here and flow this way, or you can drop in this way and flow that way. It doesn't matter. So that would be the general solution. And typically something like that would get scored 2 points, okay? You would get like 1 point for maybe your 0 slopes or your negative 1 slopes, and then you'd get 1 point for all the others in relation to each other, relative steepness. Now, you're typically going to be drawing one particular solution. So let's draw 3 of them so we can get the practice. I want to draw now the particular solution that passes to the point 0, 1. That's the point that you need to make sure that you actually land on. All right, so 0, 1 is going to be right here. Make sure we hit that point. And then from there, we just go with the flow. So notice we launch out of there to the left, and then I go horizontal. It looks like I'm approaching that. And then it launches out like that. That would be it. And that might be another check. All right, another one. Let's see, purple. I want to pass to the point negative 1.5, negative 0.5. Those should be negatives there. They're missing. Negative 1.5, negative 0.5. It's going to be about right there. Okay, so I'm kind of guessing where that point is. Now I go with the flow. As I go out to the left, notice it looks like it's doing this. And as I go out to the right, it just looks like it's exiting the bottom. Notice for each of those two solutions, it appears that this right here is a what asymptote for those two graphs? It looks like it's a slant asymptote. Very good. Affecting each of the graphs on its left-end behavior, but not necessarily on the right-end behavior. And then the last one here, let's choose beefy brown. Y of negative 1 equals 0. That's right here. What is that solution going to look like? Yeah. That one's going to look like a line. It's not going to curve at all. And it's going to be the line y equals negative x minus 1, right? It's going to pass through the y-intercept of negative 1. So you can actually come up with the equation for that one just from the tendencies of the slope field. The others you're probably not going to be able to come up with the equation of. The reason being, you can't solve this non-separable differential equation. So it becomes the slant asymptote for the other solutions, but any point that passes along that point, it becomes the equation or the graph of that equation itself. All right. Kind of fun, huh? It's almost like cheating. Like you can't solve the equation, but you still get to see what the graph looks like. Pretty nice. All right, example 3. Sketch the slope field for the differential equation, then sketch the solution curve that passes through the origin. The indicated points here, we just have 9 points. And you're not going to have to do it for an unfathomable number of points. Because if you can do it for 9, maybe 12, you could do it for many, many more. Again, it gets hard to draw differences between slopes. All right, so let's look at this one before we start. It is a differential equation, x squared plus y squared minus 1. Is that one going to be as easy to determine where we have 0 slopes? Not really. If I set it equal to 0, it's going to be a little bit harder to solve. So let's just go ahead and pick some points. The easiest point would be 0, 0. What do you get when you plug in a 0 for x and a 0 for y? Negative 1. So that's going to be like that. 45 going down. How about a 1, 0? Plug in a 1, 0. You get 1 plus 0 is 1. Minus 1 is 0. Oh, we found a 0 slope. So when x is 1 and y is 0 or the other way around, it looks like we're getting a 0 slope. Also negative ones maybe because they're squared. Let's try it. Negative 1, 0. If you plug in a negative 1 for x, you also get 0, right? I'm going to copy and paste that just to make sure it's the same. All right, let's try 0, 1. When x is 0 and y is 1, you get what? Also 0. And one last one, 0, negative 1. What does that give you? 0. So you could just kind of plug in your random points. You don't have to look for patterns necessarily, but they might emerge as you're filling it in. And now we just have the corners. When you plug in a 1, 1, what do you get? 1 plus 1 is 2. 2 minus 1 is positive 1. Okay, that's interesting. That's this 45. And you might want to copy and paste that because what's going to be the slope over here at negative 1, 1? 1, because it's squared. You're going to have the exact same slope. And then over here at negative 1, 1. And positive 1, negative 1, 1. Now look at that guy. That thing looks discombobulated, doesn't it? But I don't think we did anything wrong. Let's sketch the solution that passes through the origin. By the way, you've probably earned 2 checks. What goes good with brown? Beefy brown. Everything. Great answer. Like purple. Okay, so we got to make sure we pass through the origin. All right, I'm launching out at 45, and what am I doing when I get up here? It looks like I'm turning, right? And going down like that, right? Because there's a 0 there. This is pointing down, so it looks like I'm going to be forced down by that. And then this is horizontal, so it looks like I'm tapering back off. And similarly, if I come down this way, launch at a 45, kind of the same thing. This is kind of forcing me up and forcing me to curve around that way. So you draw it to the end. It looks like the particular solution would have what type of symmetry? It looks like it has odd symmetry, origin symmetry. Yeah, it's kind of really twisted there around the origin. That's like 3 checks maybe on a free response if you had to generate that. Not that bad, is it? Not that bad at all. Hello, Thomas. We're just doing slope fields. Okay. One of your favorites. All right, so what does the actual general solution look like if you were to do more points? We don't want to do it, right? We don't want to have to do that. Because if we can do it for 9, we can do it for 1,000,000. It looks like this. Look how broken it is around the origin. This is exactly what we did. So ours looked like it was going to be tapering off with a horizontal asymptote towards the x-axis, didn't it? But does it actually do that? No. It comes up and it actually turns around and goes back down. We didn't know that because we were only out here to negative 1. But we're not going to lose points for that because based on our information, we did it correctly. But more points, more information, the better. And that's where computers come in. Very, very twisted around the origin there. Here's what the graph of some of them look like. So ours that went through the origin really ends up looking almost like a cubic polynomial, doesn't it? Although we didn't know that based upon what was happening here. Okay. By the way, this one is non-separable, so we're not going to be able to solve it with our methods. There are advanced methods for solving things like this, but at this level, we're only solving separable differential equations analytically. And if we need to solve a non-separable one, we're going to do it how? With slope fields, graphically. Yeah. Okay, example 4. This one has 2 parts. If dy dx equals y plus 2 over x, where x is, cannot equal 0. Yeah. I don't know why the notes don't like some symbols. On the axes provided, sketch the slope field for the given differential equation at the 8 points indicated. I'm going to let you take this one on your own. I'm going to do it. You do it on your own. Don't look at me. We'll meet back here in a little bit and we'll compare answers, okay? Step 1 is to identify the 8 points. You don't want to sketch it at a point that's not indicated. Because then you have the burden of being right, and it's probably not there for a reason. that a positive slope down there? -1, -1. Try it again. If you need to actually write your ordered pairs off to the side and plug in, like make a table of values off to the side, by all means do it, because you are kind of keeping track of a lot of different things. Not bad. We are going to emphasize one little detail on this one. This one's interesting because of the x cannot equal 0 thing. Out this window, it's pretty sunny. Of course, I can't speak for the other window. Is it? Yeah. So there you have it. It's sunny outside, at least 2 windows today. So if you're going to plan a picnic, outside these 2 windows would be a good place. Mm-hmm. That makes sense. If I was to lean out and look inside that window and imagine myself looking at it, it would appear sunny. Yeah. Yeah. So, yes. All right. When we sketch slope fields, this is the important part here. Everything we've done so far has been this way. We sketch continuous curves. As soon as we hit a discontinuity, we kind of have to stop. All right? Now, here is the important part of this one. It says x can't be 0. Now, notice that if x is 0 in the derivative, I see that it's not in the domain of the derivative. That's not a problem. That could mean that I have a vertical tangent line. And a vertical tangent line, if the derivative is 0, could look like that. But when it says that x can't be 0, the function can't be 0, that means that the graph stops there. We're looking at continuous functions, and x equals 0 is also known as the y-axis. So notice then they didn't even put dots on the y-axis, so you don't want to have to draw the slope field there. So the slope field should look something like this. You're going to have a slope of 2 at -1 and 1, 0. Then you have a slope of 3 at 1, 1 and -1, 1, which is a little bit steeper. And then down here at -1, -1, and 1, -1, you have slopes of 1, which are also the same as the x-intercepts at 2 and -2. Okay, so these are slopes of 1, -1s, 2s, and then 3s. If you're drawing the particular solution that passes through the point 1, 1, I didn't draw my arrow up here, but you want to come in from the top. You need to make sure you pass through that point, and then we're going to keep going, following the curves. Now, it looks like it's, notice going from 3, 2, 1, it looks like it could be tapering off, so it's somewhere. I do it at -0, -1. It could be anywhere, though, but it's going to get closer and closer and closer to the y-axis, and it could equal anything as long as x isn't 0. So what's going to happen as soon as x gets to 0? It's going to stop. And how do you show that? With an open circle. Now, it's tempting to want to draw the solution on the other side, but we're not going to. We draw our slope fields up until we hit a discontinuity, and then we're done. Because the solution that might be over here might be a different solution. If they gave you the point -1, 1, then the solution would be on the other side. Okay? The solution would be on the other side. So we draw them up until we hit a discontinuity, and then we stop. So in this case, it would be an open circle somewhere on the y-axis. It doesn't necessarily have to be at -1, 0. It could be a little bit above, a little bit below. But you follow the trend until you hit a discontinuity. We'd have to have more information to understand if the function did, in fact, live on the other side of the discontinuity. And we don't know that information, so we stop as soon as we hit a discontinuity. Okay, so that's kind of an interesting one, but really not that difficult once you realize to stop there. All right, so another thing that we might need to do is match a slope field graph with its general solution, which is not that difficult. Now, if they expect you to spot the general solution equation, it's going to be a parent function or a transformation of it that you have to know. So let's see. If we look at this one here, Roman numeral 1, it looks like a bunch of zigzags. Do we have a zigzag equation? One that goes up and then down, and up and then down, and then up and then down. Sine and cosine, right? The sinusoids. Pre-cal started those today. So look at your answer choices. You would be given like multiple choice answers or a bank like this, Notice we have sine and cosine both as possibilities in there. Oh my gosh, which one's which? Well, it comes down to whether it's Sahala or Chala. All you have to do is drop in if you're not sure. I like to drop in at the origin right there. If I drop in at the origin, it looks like that. Yeah, it's axis high, axis low. So that would be Sahala. And notice the plus C would just move that whole thing up or down. And it would just be the family of sine functions that are axis high, axis low, axis, right? So it could represent, okay? So sine of x. They all should have plus C's on them, I guess. I got lazy and didn't type them. Okay, this one over here. If you were to drop in anywhere and kind of see what a particular solution might look like, it'll look like that, and it might look like that. Now, what's going on right here? This is where it gets hard for computers as well as humans to differentiate a slope of, let's say, 100 from a slope of 1,000,000 from a slope of infinite. Okay? I look at that and I see two possibilities of parent functions that we've studied. What do y'all see? What are those general equations? It could be a tangent, right? Very well could be a tangent. And if it's a tangent, then these would be vertical tangent lines at pi halves and negative pi halves. Could be a tangent. But it could also be what? It could be x cubed, and those slopes over here are not infinity, but it's already getting so steep that the calculator and we cannot draw them anything but vertically to differentiate. So if that's the case, you're not going to have both answer choices show up. You could have either one of them. Which one shows up here? There's an x cubed function right here. Yeah. But if that had not been there, some kind of tangent function would have been reasonable. All right, so I guess to answer the questions, we should call this one F, and we should call this one G.
Teachers and students, please find this interruption. Attention all track students.
All right, y'all do example 6. This is an actual multiple choice question.
17. It will be in the film room of the field house, ready for pickup right after school. If you have any questions, please see Coach Starnes or Coach Davidson. And teachers, if you could please turn your TVs to channel 4 for the morning announcements, or you can view them on your iPads at vhstv.com. Thank you.
You're welcome. This is an actual question. You have 5 possibilities. They don't have plus C, so this is some particular solution to the general graph given up there. Process of elimination works well. Actual question. What'd you get? A, B, C, D, or E? 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 Are y'all voting today? If you're 18, are you voting today? Sheriff? State representative? Are we all voting E at least here? Yeah. Okay. Well, in a democracy like math, more votes wins. It is E. Yes, it is E. It very well has to be E, right? Because the cosine graph would look more like that. The e to the negative x would be decay like that. That doesn't look right. The e to the x would look like that, and x squared would look like that. So, yeah, process of elimination, or just realize that, yeah, it looks like that. What would the slopes be on the y-axis, which is pinned up there against the left? They would be like vertical lines, okay? It gets pretty steep pretty fast. So, yeah, that's an easy question, right? If you're recognizing the general solution from the slope field, it's going to be one that is a transformation of a parent function. So go back and look at your parent functions. There's a catalog of parent functions at the top of the Calculus Maximus page. Now, the more fun, I think, is this type of question, where you have to identify from the slope field not the general solution or a particular solution, but the actual differential equation that generated it. These don't have to be parent functions. These don't have to be separable differential equations. There's a couple ways to do it. You can either start with the differential equation and try and match it to, or start with the graph, and match it to the differential equation, or you could pick an equation and start looking at values and matching it to a graph. Let's do that. Let's start with that. Well, actually, let's since this is A, let's just do this one first. We'll start with the graph and see if we can match it. Now that looks a lot like it could be a general solution family of what? X squareds. So if that's a family of x squareds, then the differential equation that created it must have been what? What would be the derivative of x squareds? X. So it would be maybe a linear. Do we have any linear functions down there? dy dx equals x. Could that be it? Yeah, that could be it. Just to verify very quickly here, look for your zero slopes again. Notice on this graph of the differential equation, it appears that we have horizontal tangent lines all on the y-axis when x is equal to what? 0. Compare that to your equation you picked out. When x is 0, do we get 0? Yes. Now look for trends. Look for where it's positive. Notice I have positive slopes to the right of 0 and negative slopes to the left. Is that going to be consistent with this? Yes. So that one's pretty easy. Let's do this guy. Let's start with the equation and match it now. 2 minus y. When will you get 0 slopes? When you plug in what for y? There's only one variable there. 2. So when y equals 2, you're going to have 0 slopes. What does the graph of y equals 2 look like? Horizontal line, right? Now, before you can go up there and look, because there might be more than one that has slopes of 0 at 2. What if y is greater than 2, like 3 or 4 or 5? What types of numbers are you going to get? Negative. So you're going to have negative slopes above 2, and if y is less than 2, you're going to have positive slopes. So it should go from a negative slope, decreasing, to horizontal, to positive. Now look for that graph up there. Is it anywhere? This is feasible, right? I have 0 slopes all the way through on the horizontal line. I have negatives above, and I have positives below. If that's the only one that fits that description, it doesn't necessarily matter what the scale is anymore. The horizontal line would have to be 2. That's the only one that fits. Okay, so this one matches up with Roman numeral 3, and A matched up with 4. So you could do process of elimination now. Go ahead and take the last few minutes and finish them up. Give you about 3 minutes. Hopefully it doesn't take that long. Oh, we did it the other way, yeah. All right, if you want to check, I got the answers up here. If you want to put the Roman numeral by the graph or the letter by the Roman numerals. Very quickly here, this one, if you notice, On part C, it looks like you have 0 slopes here on the x-axis, or I'm sorry, the y-axis when x is 0, because it looks like a family of hyperbolas. And it looks like you're going to have vertical slopes on the x-axis, which is when y is 0. So when y is 0, you're going to have infinity, which means you're going to have non-zero over 0. And when x is 0, you're going to have 0, which means you're going to have 0 over non-zero. So when the numerator is 0, when x is in the numerator and y is in the denominator, you're going to get this here. So which one has that? This one, x over y. Okay? And you can work backwards. When x is 0, you get 0. When y is 0, you get infinite. And notice at the origin, what happens when x and y are both 0? You get 0 over 0. That would be the single point that you would throw out. Oops, it doesn't actually exist there. At 0, 0, you would throw it out. It's hard to tell from this graph, but everywhere else it would exist. This one here looks like up, down, up, down, up, down. So it looks like some kind of trig function. If you just kind of drop in and connect the dots, it doesn't look like cosine, does it? Because it starts low, axis high. That would be a negative cosine. If you can recognize that as a negative cosine, then its derivative would be what? Positive sine. Yeah. So this would make a good multiple choice question where your answer choices would be positive sine, positive cosine, negative cosine. And if negative cosine is the general solution, then its derivative would be positive sine, which is answer choice D. This one's a good one on E. If you notice that you have 0 slopes all the way down the diagonal, so it looks like when x and y are the same sign, either 1, 1, 2, 2, something like that, you're going to have 0 slopes. When is that going to happen? Well, when x is minus y happens, okay? When they're the same, you're going to get slopes along there, so that's E. And then this one's actually pretty easy. If you just look at it, it kind of looks like an exponential function, and the derivative of an exponential function is going to be an exponential function. So e to the x is the only one that's there. But it could have been 2 to the x or 3 to the x or something like that. Any exponential function, remember, is in part its own derivative, so it's still going to be some type of exponential. All right, we'll stop right there tomorrow, and or today. We should finish tomorrow. I'll push tomorrow. I don't think we're going to work every single free response question that's on here, but I think you'll get the hang of it. Slope fields are not that difficult. They're a little bit tedious and a little bit fun. Okay?